Okay, so I'm Misha. I'm just going to introduce you. I think everyone's coming. So it's my very great pleasure to welcome virtually back, although many of you will have met her when she was here before in person, Misha Kilmer. Misha is our Kirk Distinguished Visitor on the RNT program. She's also a distinguished professor at Tufts and also deputy director of ICERM. I could probably sum up by saying what it said in her SIAM Fellow citation, where she was named as a SIAM Fellow for her fundamental contributions to numerical linear algebra and scientific computing, including ill-posed problems, tensor decompositions, and iterative methods. And so in that context, Misha's going to be bridging the divide from matrix to tensor algebra for optimal approximation and compression, which just about covers everything. Misha, the floor is yours.
course, are application dependent. And so which type of tensor decomposition we're going to use will be application dependent. But I'm using this word decompose a tensor, and what do I even mean by that mathematically? So I will cover a few of the more common types of tensor decompositions that get used in applications. To contrast this with a factorization-based method that my colleagues and I have developed to try and draw some distinction among the different kinds of tensor factorizations. In the matrix-based case, we have notions of what is a low-rank approximation, how, in what sense is it optimal? Can we do that for tensor decompositions? And can we prove my hypothesis that basically we gain if we can manipulate the data in tensor format as opposed to unwrapping it into a matrix and treating it with matrix methods. So to set the notation, in fact, we've already encountered tensors, maybe didn't realize it, but a 0th order tensor is really just a scalar. A 1st order tensor would be a vector, a 2nd order tensor would be a matrix, but a 3rd order tensor and beyond is where it starts to get interesting. So a 3rd order tensor would be a 3-way array, a 4th order tensor, a 4-way array, and so on and so forth. So throughout this talk, I'm going to be focused on 3rd order tensors because that sort of already stretches the limits of what I can convey on these slides. But much of what I'm going to describe actually will generalize to higher order tensors as well. Throughout the talk, when I'm applying norms to these high order tensors, then I really just mean a generalization of the Frobenius norm. So it would be the square root of the sum of the squares of the magnitudes of the entries. So in terms of the perspective I'd like for this talk, I took a tensor, a 3rd order tensor, and I chunked it up in 3 different ways. And there are more ways that I could do this, but these are the ways that are most relevant. So if I slice the tensor front to back, you observe that each frontal slice of a tensor is a matrix. If I slice it left to right, then those lateral slices are also matrices. If I chunk it up into smaller components and basically look into the 3rd dimension, those objects are called tube fibers. So basically, the thing that I would like for you to have in the back of your head is that I can look at a tensor, a 3rd order tensor, as if it is basically a matrix of these tube fibers. So if I took the tensor and turned it front on, it would look like a standard matrix if you didn't see the 3rd dimension. And likewise, if I slice it up into this lateral dimension and twisted it so you didn't see the 3rd dimension, it would resemble vectors. So I'm going to be using those notions a little bit later on. In places where I need to reference into entries in the tensor, I'm using a MATLAB-like notation. So for example, a lateral slice, the jth lateral slice of this 3rd order tensor would be obtained by basically holding the jth index fixed, and the colons means take all the rows and all the dimensions into the 3rd dimension. So we want to find a way to express our tensor that leads to the possibility of compressed representation, but we don't want to throw away important features in the original tensor. If we go back to what we know in the matrix case, the traditional workhorse, the thing that we teach our undergraduates right away is the singular value decomposition, right? The singular value decomposition of an n by n matrix always exists. It's this factorization into orthogonal matrix U, diagonal matrix S, orthogonal matrix V. And I can take and express that matrix factorization also as a sum of rank 1 outer products. So that I have in this summation expression here. And one thing that we know is that if we want to find an approximation to the matrix A, and we want to do it in an optimal way in the Frobenius norm, with a matrix that has rank P, where P is less than the rank of the matrix A, then singular value decomposition just gives it to me, right? I just need to truncate this summation to R terms and instead take P terms of it. The singular values are arranged in non-increasing order, so I'm basically throwing away the terms that have the least amount of energy and retaining the terms that have the most amount of energy, and that gives me an optimal approximation. And if I wanted to, depending on the size of P, I could choose to store B implicitly using just keeping the singular triplets, and that implicit storage format gives me a compression. So instead of mn numbers for storing all of A, I'm storing B, the singular triplets that make up B, and that saves me. So what is the extension of this to higher dimensions? Going back several decades, the first, probably in the literature, notion of how to generalize matrix SVD to higher dimensions is a handy comp parafact decomposition. So the idea is, instead of so sort of generalizing this vector outer product to 3 dimensions now. So these little chicken feet here, they are individually identified as rank 1 tensors. And so the idea is trying to find an approximation to the tensor X, which can be expressed as R of these rank 1 tensors. So when this gets used in practice, people like it because it can be very interpretable. The blue, the magenta, and the green colors have some maybe physically meaningful things according to their what they're representing on those different axes. But a lot of strange things actually happen when you try to use this type of approximation. For example, unlike the matrix case, if I wanted to replace this approximately equals sign with an exact equal, if I wanted to find the smallest value of R for which that tensor X can be approximated as a sum of rank 1 outer products, that's actually an NP hard problem. So we're not going to be able to do that. So unlike in the matrix case, when it's a polynomial in time and can be done, in the tensor case, it's NP hard. The other issue has to do with the fact that I could pick a rank R and try to solve this optimization problem. And the typical workhorse for that is something like an alternating least squares. You can fall into local minima. In fact, I could get a sequence of rank R approximations that converges to something which is rank R plus 1. So there are all kinds of issues with it, but it does work in some applications very, very well. This is one demonstration in a paper where the representations have this physically meaningful interpretation in terms of time, trial, and neuronal factors. Another generalization that you'll see in the literature that's quite popular is something called the Tucker-3 decomposition. And that is an approximation of the tensor into something called a core tensor. That's the script G here. And 3 factor matrices. If the factor matrices have fewer columns than rows, then we have a compressed representation of the tensor. So we just need to store the core, which is K1 by K2 by K3, and the 3 factor matrices. In this case, we can actually put orthogonal constraints on the factor matrices. So we might require, say, that the columns of A are orthonormal. And you could actually replace this approximation sign with an equal sign and find this factorization in polynomial time. It's just a matter of unfolding the tensor 3 different ways and taking matrix SVDs, and that will give it to you. You could truncate along each one of those modes and get sort of an analogy to the matrix truncated SVD. However, if you do that truncation is not optimal approximation in the Frobenius norm. So we don't hit that even in this case either. But in some applications, it works really well as a higher order principal component analysis type approach. There's some usefulness to having the orthogonal factor matrices, for example. And in many applications, it's been shown to be highly compressible in spite of the fact that truncating to K1, K2, K3 terms is not optimal. And many examples of where this is useful in practice. One of them is in, for example, latent semantic indexing. If you start digging into the tensor literature, you find an entire alphabet soup of different decompositions, and some of the other popular ones that come up in searches would be the tensor train or the TT decomposition, the hierarchical Tucker decomposition, and so forth. One nice feature that the CP decomposition and the Tucker decomposition have is that they're essentially orientation independent. So if you permuted the cube in some different way, it's just analogous to permutations of the factors. It's and again, these different methods will pick up different structures that are inherent in the data or the operators where they're used. In the CP decomposition, you don't necessarily, the rank can actually exceed any one of the 3 dimensions, so you don't get orthogonal factors. So you might not want to use CP when you could use HOSVD. There are just various trade-offs. But none of these, until the work that my co-authors and I came up with, really led to a linear algebraic framework. In the sense that, hey, the matrix SVD, I could first factor the matrix into a product of matrices, and then I could take that product of matrices and I could write it in outer product form. We don't have that with any of these methods that are listed here. So what I want to move towards now is this algebraic framework for tensors, really thinking of them as operators on other tensors in the same way as we can think of matrices as operators on other matrices and vectors. That means I'm going to have to introduce a notion of what is it to multiply 2 tensors together. And if I can nail that, then I should be able to build the rest of the framework around that. And tell you what that means. What is an identity tensor? What is a tensor transpose? What does it mean to say a tensor is orthogonal, and so forth? And building on all of that, we can build up to tensor-tensor singular value decompositions that are reminiscent of these matrix-based singular value decompositions. I'll be able to prove an Eckart-Young theorem, in other words, an optimality in terms of our decomposition, our tensor singular value decompositions. And I'll be able to prove what I claimed at the start, which is that it's better to work in tensor forms with tensor decompositions in terms of compressibility than standard matrix. And I'll filter in some applications throughout. So the key here is this concept of matrix mimeticity. So we're gonna, if we understand the linear algebra, then all we're gonna do really here is add a dimension, right? So where we had a scalar, a vector, and a matrix, we now are going to think in terms of a tube fiber, a lateral slice, and a tensor. So those are our tensor analogues. And whereas matrices are linear operators, we're going to call tensors T-linear operators, the T's just for tensor, and the fact that I'm not a particularly creative person when it comes to naming conventions. So. All right, so there's a lot on this slide, but it's at the heart of the talk, so let me take a moment and explain. The first thing I'm going to need in order to be able to define a product between two tensors of appropriate dimensions is an invertible matrix M. So if I have, let's say my tensor script A is M by P by N, and B is a P by L by N tensor, and I want to define a multiplication between those two tensors, M is going to be an N by N invertible matrix. So this notation with the times and the 3 subscript, that's called a mode 3 product. And what it means, although we compute it differently in practice, but mathematically, the way you can think about it is a tube fiber. So that is basically a vector of length n into the board. So the times 3m means take every tube fiber in the tensor A and apply m to that tube fiber. In other words, do a matrix vector product. Okay. The resulting tensor, after I've done that to every tube fiber, I call that A hat. Because M is invertible, I can always recover A from A hat by applying the inverse operator along tube fibers. Again, that's just basically a matrix vector product, a whole bunch of matrix vector products with M inverse. Okay, so now that I have that, I fix M, and this star M product between tensor A and tensor B is defined by taking A and B, making their corresponding A hat and B hat tensors. We call that taking the tensors into the transform domain. Then we do, from front to back, we are going to do independent matrix vector products. So A hat, the first frontal face, and B hat, the first frontal face. I do a matrix-matrix product there, and I do the same thing all the way. Those are independent. They can be done in parallel. And then the resulting tensor, call it C hat, I apply M inverse to the tube fibers, and I get back my resulting tensor script C. Okay? And if I wanted to say, implement this in MATLAB, then this is, how I could do it just in terms of indexing. what this means is it is really matrix mimetic. So in the sense that if C is defined as A star MB, then I want to look at, say, the jth lateral slice of this tensor C. It's really this T-linear combination of the lateral slices of the A tensor post multiplied by the tube fibers in B. So again, if I took this picture that I'm displaying here and I took away the aspect in the third dimension, it would look exactly like the definition of what the jth vector in a matrix looks like in terms of the A and the B. Entry-wise, you know, same thing, right? If I wanted to compute the 2-3 entry in the product, I really need the second row of the tensor on the left and the third column of the tensor on the right. And it can be computed in this way. So that feels really good so far. In terms of what's going on under the hood, remember M is already fixed. So the multiplication will change if you change M. So imagine M is fixed. Computing the simplest thing, the action of, say, 2 tube fibers under the star M product, it turns out to be, you could write it out equivalently by basically thinking of the A as a vector, as a row vector, and post multiplying it by a structured matrix, where the structured matrix that you're post multiplying by actually depends on the M that you've defined, right? Likewise, if I want to look at the next highest level operation here, a lateral slice star M product with a tube fiber, that turns out to be equivalent to taking that slice and reorienting it as a matrix and post multiplying that matrix by a structured matrix that's generated by the vector B. So one way to think about or one example for this is that if M is a discrete Fourier transform matrix, then this structured matrix here will just be a circulant matrix generated by the vector B. And what that means is that this tube-wise multiplication, if M is a DFT matrix, is really just discrete convolution, which is and it means that tube-wise operation is commutes. Okay, so that's what I needed to be able to move forward with the framework. So now I can, define what I mean by an identity tensor. The identity tensor would be a M by M by N tensor, and you notice that N is the one dimension that's the same throughout. So this is an orientation dependent factorization. And I can, tell what conjugate transpose means under this star M product. And I have a notion of what it means for a tensor to be unitary or orthogonal under the star M operation as well. Another familiar fact, which is also very nice, you're used to saying if I have two matrices and I multiply them A and B and take the transpose, it's the product of the transposes in reverse order. I get that here under the star M product as well. Now, if I were earlier, to define star M, all I need is an invertible matrix M. But if I take M and I restrict it to a non-zero multiple of a unitary or orthogonal matrix, then if Q is unitary under star M or orthogonal under star M, then the Frobenius norm is preserved under multiplication by a unitary or an orthogonal tensor, which is a really nice feature because it suggests that now we can, in fact, get to our notion of a tensor singular value decomposition. And here it is. So if I have a tensor A, which is m by p by n, and I choose m to be a non-zero multiple of a unitary or an orthogonal matrix, then that tensor will have a full tensor singular value decomposition where I have u as a unitary, v is star m unitary. The S tensor is what we call face-wise diagonal. So here is a cartoon of what that would look like. So again, if I would take the S tensor and turn it face on, it would just look like a diagonal matrix to us in perspective. Moreover, I can imagine the U tensor, again, carved up as lateral slices. I can take the VH tensor, carve it up as horizontal slices. And I can take this factorization and write it out in summation form so that I essentially have something that looks, literally looks like an outer product of these tensor factors. So this lateral slice of U is playing a similar role to a column of the left singular matrix in a matrix SVD. A horizontal slice in VH is taking, is playing the role of the right singular vectors. And the S sub i's, these tubes, are playing the role of, you know, we have singular tubes instead of singular values. However, the singular tubes have this relationship to one another. They are, in the Frobenius norm squared, ordered in terms of non-increasing order. So they carry an energy association with them in the same way singular values do for the matrix SVD. And so if I only have R tubes, which are non-zero, then this would be that's the cartoon representation of what I was just saying. It's basically this outer product looking thing. And yeah, the T rank in this case is then the number of those non-zero singular tubes that I'm keeping. This is different than the CP rank, I should mention that. But here's now our Eckert-Young theorem, which says if I were to take my tensor SVD under star M and I truncate it to kappa terms, then it gives me an optimal approximation in the Frobenius norm over the set of all approximations that I could get, which are essentially this outer product of tensors under the star M factorization. Again, M has to be fixed. Once M is fixed, the decomposition is fixed and the approximation is fixed. So different M, different decomposition, and possibly different error in the reconstruction. So the way that this is computed in practice, it's actually of practical importance too, is that I start with a tensor A. I take it to the transform domain by, you know, at least mathematically, I'm applying M to all the tube fibers. That decouples the problem. So now I just go front to back in A hat. I do a matrix SVD on each frontal slice. That gives me a U hat, an S hat, and a V hat tensors. And I truncate those to kappa terms in each case. And to get the U kappa, S kappa, V kappa, I just need to apply M inverse along the tube fibers, which again, the value of this really comes in using M being a non-zero multiple of an orthogonal or unitary transformation. So really M inverse is, not any more expensive than applying M transpose or M Hermitian transpose. So, okay, that gives us some sense of how I might use the tensor SVD for a compression. But I really need to maybe try and convince you that I can get something better from this kind of compression than from, again, unrolling the data as a matrix and doing a matrix approximation. So here are three matrices. I could unroll each one of those three matrices as a column and make a big, tall, thin matrix, or I could put them in as lateral slices of a tensor. And I want to convince you that decomposing the tensor on the right gives me an advantage. So what we were able to show is, again, fix M, and under that star M approximation, truncate our decomposition, our tensor SVD to K terms. Then the error between that K term approximation to the tensor A is less than or equal to the error between treating that exact same tensor script A as a matrix, that was the unfolding in the cartoon I had on the last slide, and computing the matrix-based SVD and taking the matrix-based truncation to K terms. And what's important here is that strict inequality is A, it's achievable, that this result holds for any M that is a non-zero multiple of a unitary orthogonal matrix. I won't go into the proof of why this works, but it's because I can take the matrix SVD and write it in the star M product framework. And the reason I can get strict inequality is because I'm able to take advantage of latent structure in the data that isn't present, that we don't see if I unwrap it and treat it in this matricized form. And here's just a really simple example. Here's a tensor A, and here's the matrix version of that tensor. And if I truncate to one term, I can get an exact representation here. But if I use a matrix SVD, this is not rank deficient, so the error is not zero. And what is nice now, I've got the whole framework, the whole setup to be able to think about these tensors in the way that I'm used to thinking about them, in terms of matrices, right? I can define orthogonal projections, for example. And one application where one of my former PhD students was able to show that this is useful is in facial recognition, for example. I can just keep my basis tensor here, my UK, and then when I need to compare new images, I looked at the expansion coefficients under this tensor and see to which one am I closer to. The TSVDM, though, does ignore some relative importance in the faces. If I just truncate to K terms, what it means is that in transform space, I'm treating every one of these independent matrix factorizations completely independently. It turns out to make more sense if, when I do these matrix SVDs, if I compare all of the singular values in each one of these faces to one another. And I truncate based on their ordering. So in this cartoon, I've shown that maybe in the first frontal slice, that I have 5 really large values, and the second one 3, and then the remaining 2, I have just 1. So maybe I just want to keep those for those blue singular values and their corresponding singular vectors. And I can do that. We call the representation the TSVDM2 because it's a second order approximation here. But it turns out that this is even more compressible yet than the TSVDM. In fact, if you give me a truncation value kappa, I can find a corresponding multi-rank row for which I can find this tensor decomposition, and I can again achieve inequality here in almost all interesting examples. Just to give a sense of the fact that this star M product is taking advantage of latent structure. Here is the compression ratio versus relative error in approximations for different values of the truncation index on a Yale faces data set. So I can take different choices for the M. I can take a discrete cosine transform. I can take a Haar wavelet transform, or I can just try to take like a random orthogonal matrix. And what we see is that in the case where I take M to be the discrete cosine transform or the Haar wavelet transform, I get really good compression even for small relative error. On the other hand, it far outstrips what I can do just treating that same data in a matrix-based traditional form. And it's not too far off from treating from doing the truncation of the tensor-based, but using M being a completely random orthogonal matrix, right? You don't expect that M to have any structure, and because it doesn't have any structure, it doesn't really buy you anything in terms of using a tensor decomposition. There are relationships that we can draw between the higher order SVD and our tensor decomposition, for example. So this is an HOSVD, full HOSVD of a tensor A. This third factor matrix Z is what's going to be important. So it's an orthogonal matrix, n by n orthogonal matrix. And it turns out that if I then take my M and define it in terms of the Hermitian transpose of that orthogonal tensor, and then I can make a claim about how compressive our approximate tensor SVD is relative to the higher order SVD approximation. In other words, it gives me a better relative error for that kind of truncation. So it's not quite a statement about the compressibility, but it does say, it gives us a way to compare apples with apples. One application that I'll show you is compressing hyperspectral data. So this is just a few snapshots of the images of the Washington Mall in hyperspectral wavelength. And if I do compare the tensor SVD method using M defined by the one of those matrices in the higher order SVD, you can see the comparison here between our method and the standard matrix SVD truncation. This is compression ratio again versus relative error, and you want to be on this top curve, which is where we are. The colors here indicate that we're taking truncation values which are as close as we can make them, given that there are two different types of decomposition similar in nature. We can change around some parameters. The reviewers of the paper asked us to do a whole bunch of different experiments. And in every case, we could basically show that our method here leaves us on this top curve and is far more compressible than the higher order SVD. And there's, again, I mentioned the tensor trains. There's something called the tensor train SVD, which is a bit more competitive than the higher order SVD, but more often than not, our method is an improvement on that type of compression. So far, I got through this introduction to a tensor-tensor product and an associated framework that's been introduced. It is very cool. I mean, this is some of my work of which I'm most proud. It leads to algorithms that are really reminiscent of matrix versions of those same algorithms. You could, define your star M product, and then you could go into, say, MATLAB and overwrite different operations and have a whole suite of tensor factorizations. We were able, none of the other tensor decomposition methods that I mentioned has an Eckert-Young theorem associated with it. We've been able to give Eckert-Young theory for this whole family of tensor SVD factorizations. And we've been able to prove this claim that, we do better with tensor factorizations than with corresponding matrix factorizations when you compare those in SVDs. The code everything here is highly parallelizable, and we've been able to extend this to using randomized numerical linear algebra to get things even faster. This notion of tensor-tensor product does extend to higher dimensions, essentially by recursion. As I mentioned, we gave this theoretical comparison to the matrix approximation, which solved this open problem. And we can compare theoretically and in practice our method to other tensor decompositions that are more popular and in use. As I noted, that the original work, when I started this with Carla Martin, we took M just to be the DFT matrix. And under that specific choice of M, we've been able to do a lot of fun applications. We can do proper orthogonal decomposition for reduced order modeling and dynamical systems. We can define tensor-based nuclear norms and do data completion problems. We can use it for regularization and multi-energy CT. And others have jumped on the bandwagon. They've talked about what it means to have eigendecompositions under the star M framework, and what does it mean to identify tensor-based functions, and so on and so forth. More recently, there's been this code that's based on our TSV DM2, where they've been able to use this method to do dimensionality reduction, physically meaningful dimensionality reduction on longitudinal omics data. So that's been nice to see. But a lot of other questions remain unanswered. The compression you get depends on M. How do we find the right M for our application? Can we learn it? Can we do better than these inequalities if we know that our data has specific features? We say something about that gap. How do we do the comparison to our factorization in higher order case? One other thing that we've been able to observe in practice, we can build, say, neural networks, tensor-based neural networks based on this new framework. And we've been able to observe that we need less training data in this case. Can we prove why that is? And if a third order is better than a second order is a higher order better than a third order tensor? Should we be looking for even yet more structure in higher dimensions than what I've mentioned here? I don't know. It's an interesting question. Sometimes it keeps me up at night. So with that, I will finish, and thank you for your attention, especially for this remote format of the talk.
And your tensor formulation, of course, puts us in mind of lots of rich tomography problems, including the one you mentioned of spectral types of tomography. Any questions?
First of all, thank you, Misha, for a very interesting talk. I have the following questions. There is a lot of activity recently, both in matrix and especially in tensor versions of complexity theory, complexity of various estimates of complexity of various types of calculations, starting with still unresolved matrix multiplication. But there is a lot of activity in tensor field now, for instance, due to Landsberg. Does your study have any side related to complexity?
Wow, that's a good question. I actually am not, I don't know. I don't know the answer to that. That's another one I'll have to add to things to think about.
Okay, more questions? Can I ask something that, I mean, I was thinking perhaps we have a tensor per voxel, like strain tomography or something like that, and we might have many dimensions in our measurements. We might be taking, you know, a diffraction pattern per ray. So both the data and the unknown, say, image, might have a different tensor structure. And you mentioned briefly inverse forms, but it seems we've been concentrating here on the, you know, a data or an image being a tensor. Can you say anything about an inverse problem where both the data and the unknown are tensors with different structures?
Okay, so I'm not, tell me if this answers your question or not. So if I imagine, for example, a de-blurring problem where the operator is a block circulant matrix, for example, I can write block circulant matrix times a vector as like that's the model for the blurring. But I could also write that under the star M product. I could write that as an operator applied to another tensor using that structure. So this is possible. That's one possibility. And you know, I could, maybe I have to process the images, or a sequence of images. I have to process them somehow differently, and I represent the operator action under a specific star M. So that can be done. But I don't know if that's really answering.
Yeah, I don't know. I mean, you know, one question is what's the appropriate M for you know, specific problems, and I guess well, maybe I'll have to have a Zoom call with you to see if I can formulate something. So anyone else questions? Yeah, Josh.
In terms of the software implementations you mentioned, what kind of stuff can that currently do? Like, can it go? Can it handle above the 3D case, for example?
Yes. So everything is parallelizable, which is very nice. So I have code for higher dimensions. The seismic data completion problem that I mentioned briefly as an application, that was a 5-dimensional problem. But the graduate student that implemented that, I think, did it all in parallel MATLAB. So that bulk of the operations are done in this transform space, essentially, where everything decouples, and that's where you get the parallelizability, which is really nice. So maybe I should mention in terms of the complexity to do a tensor SVD, if you use a fast transform, for example, to define your M, the complexity, if you write in big O, would be the same for the treating the matrix, the data as a matrix as it would as a tensor. However, that doesn't mean that they're created equal in terms of being able to compute them, right? Even if you had a sequential computer, a sequential implementation, the ability, I could, because everything breaks down in a parallel form, the big O doesn't tell the whole story, I guess is what I'm trying to say, right? You still might not be able to actually, it might be so large that you can't do the matrix-based SVD where you can do the tensor-based SVD because you can use the fact that it's decouples in the transform domain. So.
Thank you.
Any more questions? In that case, I mean, so I do hope we can at least virtually talk to you as a follow-up. That would be lovely. We're going to have wine and beer and nibbles, I think. Now. So I'm sorry you don't get that.
Yeah, somebody's going to have my share.
Lovely to see you, and thank you very much for a very nice talk.
Thank you.